Hello and welcome to the YouTube channel of Canberra Engineering College. In this video session, we will study regarding a stable multivibrator. So we already know what is a multivibrator and we have studied regarding the construction of IC 555 timer IC, which is basically used to build a multivibrator circuit. We have also built a monostable multivibrator circuit using IC 555 timer, and we have studied regarding the various time durations during which it will be turning on and turning off. In this video session, we will check regarding a device or a circuit which is called as astable multivibrator. As the name says, astable. Astable means this particular circuit doesn't have any stable states. The output or the oscillations, whatever that is produced by this multivibrator, will be unstable, or there will be no stable states at all, which means that it keeps changing its state from high to low or low to high. After some time, maybe you can call this particular stable multivibrator circuit as a free running multivibrator, or you can also call it as a rectangular waveform generating circuit. So there are different names in which you can address this particular multivibrator circuit. One of the name is called as free running multivibrator circuit, and other one is actually rectangular waveform generator. Very similar to the things what we have seen in the previous monostable multivibrator. This astable multivibrator doesn't need any external triggering pulses. You would have seen in case of your monostable multivibrator, there was a pulse which was given to this particular pin number 2 or pin number 2 of this particular IC 555 timer. But in case of your astable multivibrator circuit, there are no trigger inputs, or you need not give any trigger inputs in order to change the state of the output. So the circuit is what you can see here. So as always, uh, the thing what is drawn after this dotted lines, this is actually a 555 timer. So you have a comparator circuit which is made up of op amp. You have got 3 resistors which form a voltage divider network. You have a flip flop. You have a discharge transistor. You will be having the outputs which will be connected to the output side, and all the things which are a part of a IC 555 timer. In addition to that, we have connected 2 resistors RA and RB and 1 additional capacitor to a IC 555 timer, so that you form or you get a stable multivibrator circuit. Now, in order to understand the working of this particular circuit, we need to divide the time duration or working duration of this into T on and T off. T on and T off are with respect to the transistor that is connected here. That is with respect to the discharge transistor that is connected here. For example, if I go with the 555 timer simple circuit, you can see here. This is your 555 timer circuit, and this are the additional resistances and capacitors what are connected in order to form a stable multivibrator circuit. So let's say during on time, let's say as I said, I'm going to divide the operation into 2 different states. One is on time operation and other one is off time operation. So let's say it is on time operation, okay. At on time operation, that is, let us say at t is equal to 0. That is at t is equal to 0. And let us say my capacitor is not charged. Let us say the capacitor what is connected here is not charged. This same capacitor voltage what is 0 is applied to 2 terminals of upper and lower comparator. So you are applying the output voltage or the voltage what is actually 0 to the comparator, that is upper comparator and the lower comparator. That is, you are applying it to the trigger point of the lower comparator and threshold point of the upper comparator. As the capacitor voltage Vc is equal to 0, as the capacitor voltage Vc is equal to 0, this voltage is obviously less than 1 by 3 Vcc, right? This voltage is obviously less than 1 by 3 Vcc. As this voltage Vc is equal to 0 is less than 1 by 3 Vcc, your lower comparator will turn on. Your lower comparator will turn on. As this goes on, you can see this will become 1 and this will be 0 because this is still off, right? This output, the input to the flip-flop R will be 1 and S will be 0, because of which Q bar will go high, because of which Q bar will go high and Q will remain 0. Now, after this causes, or the output of this particular transistor causes the transistor T to go off, obviously, right? When Q bar is 1 and when Q is equal to 0, the discharge transistor will remain off. After this remains off, now concentrate here. As this is turned off, the voltage what is flowing from the voltage source doesn't find any alternate path to flow. Because of which the voltage will be flowing through this path itself, because of which your capacitor will start to charge. Through RA and RB. Because of this transistor remaining on, your capacitor will start to charge through the path RA and RB. So it is actually 0. After 0 it has to increase, right? After 0 it has to increase to a particular value. To be very frank enough, your capacitor will charge to a value of VCC, because VCC is the supply voltage what you are supplying, right? So it will charge to VCC. On the way of charging, it will cross something like 1 by 3 VCC, and it will cross 2 by 3 VCC, and finally it will become VCC. As soon as the voltage in the capacitor crosses 2 by 3 VCC, as soon as the voltage of this particular voltage crosses 2 by 3 VCC, your on time is terminated. Your on time is done. Now it enters a stage called as off time. So what happens during the off time is the voltage of the capacitor will be exceeding 2 by 3 VCC, because of which your upper comparator will turn on and your lower comparator will turn off. So right now this will turn on and this will turn off. Because of upper comparator turning on, S will become 1 and R will become 0. As S becomes 1 and R becomes 0, Q bar will become 0 and Q will become 1. When Q becomes 1, this transistor T will turn on. As the transistor T turns on, the capacitor what was been charging to VCC will start to discharge through the resistance RB, through the transistor T. You are getting this point? As the capacitor was charging, and once the voltage across the capacitor has crossed 2 by 3 VCC, transistor T will turn on. Once the transistor T turns on, the capacitor will not get any voltage through this particular path. The capacitor will not get any voltage because it is finding an alternate path. As soon as the capacitor is not getting any charge, what should happen to the capacitor? The capacitor should start to discharge. It will start discharging through the path RB and to the ground. The time taken by the capacitor to discharge from 2 by 3 VCC to 1 by 3 VCC, because your capacitor is right now 2 by 3 VCC, right? So it will discharge right now. It will discharge through 1 by 3 VCC. And this discharge time depends on the capacitor value and the resistance of RB. Because it discharges through this path, right? It discharges through this particular path. Now as it discharges, it will discharge to 1 by 3 VCC. As it becomes 1 by 3 VCC, your lower comparator will turn on and your upper comparator will turn off, because of which my transistor will once again turn off, and this cycle is going to repeat. Which means that if you take the capacitor, your capacitor voltage was 0. As the capacitor starts to charge, it started to charge and it reached 2 by 3 VCC. As it reached 2 by 3 VCC, your transistor will be turning on, or this particular path will be open, and because of which your capacitor will discharge and it will reach 1 by 3 VCC. As soon as it reaches 1 by 3 VCC, your lower comparator will turn on and it will once again start to charge, and this process is going to repeat. Also you can observe that once the capacitor charges and discharges, the output of this particular flip-flop, which is actually the output of a multivibrator circuit, will become 1, will become 0. It will become 1 and it will become 0, which can be clearly observed in the next waveform. You can see here. See here. This is 1 by 3 VCC. During 1 by 3 VCC, it is high and it is going to remain high until it becomes 2 by 3 VCC. Once it becomes 2 by 3 VCC, you can see the capacitor discharges. By the time your voltage reaches 2 by 3 VCC, you can see the output of the device also going low, and it will remain low until the capacitor discharges to 1 by 3 VCC. As it becomes 1 by 3 VCC, it will turn on again, and this cycle is going to repeat. So this is actually the voltage of the capacitor, and this is actually your output of the multivibrator circuit. I call it as stable because none of the states are stable. It remains stable for a particular time, but it is not stable constantly. It is stable for only a particular amount of time. After that, it becomes, or it goes low. It becomes low. So this is what is your circuit, or this circuit you have it in the lab also. This particular circuit you study in the lab also. So basically here capacitor is the person who makes your output go high and low throughout, or capacitor is the main component which makes your circuit go high and low. Now what we need to do is, suppose if I say this is TC and this is TD, isn't it? This is TC and this is TD, or I can say that this is turn on time and this is turn off time. So this is actually your turn off time, okay? This is actually your turn off time. So what you can write? You can write T is equal to, you can write T is equal to T on plus T off. Quite obvious, right? Or you can write it to be equal to T charging plus T discharging. You can write it. Or this is the time period. This is the time period. If you want to write the frequency, you can write it as 1 over T, which is equal to 1 over Tc plus Td, right? So this is your frequency. Now what you want is, let's find out the voltage across the capacitor. Let's find out the voltage across the capacitor. The voltage across the capacitor is given by this equation. See here, frequency is given here. The voltage across the capacitor, that is voltage across the capacitor, is given by the initial voltage on the capacitor is 0, because at time t equal to 0, everything turns out to be 0 here. E to the power minus 1, that is 1, 1 minus 1 is 0, so Vc will be equal to 0. So the formula for capacitor voltage is given by Vc is equal to Vcc into this formula you have checked out previously also, e to the power minus t by Rc. Now let's consider, or if there is some initial voltage, or if you say that if there is some initial voltage, you can consider it to be, you can consider this particular formula also. You can consider this particular formula also. But what happens initially is, initially as you considered Vc is equal to 0, as you considered initially Vc is equal to 0, but to be very frankly speaking with respect to the circuit, if you check the voltage here, your capacitor voltage has never come to 0. It is 1 by 3 VCC, isn't it? It is 1 by 3 VCC. We'll consider the same thing. Taking the same thing here, we will substitute this values. We'll substitute this value. Vc will be equal to 2 by 3 VCC. This final voltage will be VCC. Initial voltage will be 1 by 3 VCC minus final voltage, which is VCC into e to the power minus T C divided by Ra plus Rb into C. So this is actually the voltage what your capacitor has displayed during the turning on. So this is your capacitor voltage. This is your final voltage which capacitor should reach. This is your initial voltage. This is your final voltage. All the values are substituted here, and this T will be taken as Tc, because I am speaking about the charging time, right? T will be taken to be equal to Tc, and charging will happen through which path? Charging will happen through Ra and Rb. Charging will happen through Ra and Rb. That is why we have considered Tc divided by Ra into Rb into C. And substituting that and simplifying, we will get turn on time to be equal to 0.693 Ra plus Rb into C. This is actually the charging time of your multivibrator circuit. Very similarly, if you substitute the same to the turn off time of your capacitor, that is final voltage during the turn off is 1 by 3 VCC. This is 0. That is 2 by 3 VCC and everything is 0 here. And if you substitute that, and you can observe from the circuit, discharging will happen via which? Discharging will happen via RB. Charging will happen via RA and RB, right? Keeping that in mind, the discharging time constant can be found out by substituting all the required parameters in the equations, and you get T of to be equal to 0.693 RB into C. Total time period is what we have already seen, right? TC plus TD. So 0.693 RA plus RB into C plus this particular term. So total time duration taken by the, or total time period for the stable multivibrator circuit to show one complete waveform is given by 0.693 RA plus 2 RB into C. Duty cycle and all, you can calculate it easily. Once the time duration is known, you can find out the frequency, and once the frequency is known, you can find out the duty cycle also. So this is regarding your stable multivibrator circuit. So normally if they ask you any questions, probably those questions will be on this particular stable multivibrator circuit, because this is a part of your lab experiment also. So you need to write the circuit, you need to write the on time working and the off time working, and you need to derive the turn on time and turn off time of the stable multivibrator circuit. So that is this particular formula. Coming to the application part, you can use this particular stable multivibrator circuit to generate waveforms which is square wave, or you can use it in the split trigger circuit. Split trigger is actually one of the very important application of your IC 555 timer IC, and voltage controlled oscillator. Voltage controlled oscillator means you can control the voltage. What is the output voltage you are expecting, and what is the minimum and what is the maximum voltage what you are expecting. That is what is called as voltage controlled oscillator. Thank you.